Hi everyone, my name is Sean Sinclair and I am a second year PhD student at Cornell University in the Department of Operations Research. Today I'll be presenting on some of my work for adaptive discretization for episodic reinforcement learning in metric spaces. And this is work that I did with my two advisors, Sid Banerjee and Christina Yu, both of whom are also at Cornell University in the Operations Research Department. Just to start us off, I kind of want to go over the main contributions of this presentation. The first of which will be that we were able to develop an efficient algorithm for reinforcement learning in large state and action spaces. And the second is that we were able to reduce the memory requirements of common reinforcement learning algorithms by only discretizing important regions of the space. And hopefully throughout the presentation, I'll be able to touch back to these two main contributions. I want to start us off with potentially a little bit of a cartoon example, but hopefully it sheds light on a lot of interesting control problems in operations research, and hopefully highlights a lot of the tools and strengths that reinforcement learning can have for these problems. So pretend that we are in Las Vegas. So we are in the Las Vegas Strip. So we have the unit interval 0 on the left-hand side and 1 on the right-hand side. There's a bunch of different hotels kind of spread out across the Las Vegas Strip, and we are an ambulance operator that's trying to navigate and control optimally on this Las Vegas Strip. So initially, at the start of the day, as the ambulance operator, we get to decide on a location that we want to station the ambulance, paying a transportation cost in order to station the ambulance at that specific location. Afterwards, a random request for a sick patient is realized, and we have to pay an increased travel cost in order to go and travel and service that patient. This process then repeats, where we decide on a location to station the ambulance, a random request is realized, and we pay an increased cost in order to travel and service that patient. And this might be a little bit of a cartoon example, but hopefully it shows how reinforcement learning can be used for a lot of resource allocation problems. And just to name a couple, you could think of a queuing system where the queuing server has a lot of different service rates that it could be running at. And you're trying to learn an agent that decides if there's this many people in the queue, which service rate do I want to run the system at? Another situation could be controllers for short-term memory. So you could think of a dynamic memory system where you're trying to train a controller that decides the sequence of cache memory access requests that it wants to serve in order to minimize the waiting time potentially, while also ensuring that the cache has some structural integrity. And another situation could be scheduling algorithms and processor assignments for data centers. And so just to kind of get us into the reinforcement learning setup, reinforcement learning is a general model where an agent is interacting with an environment that has unknown rewards and stochastic transitions. So the agent is given an initial state, and it then picks their action, after which a new state and a reward is realized. And just to kind of put this into the perspective of the Las Vegas example that we had before, the initial location was the starting location for the ambulance. The action was the location that the operator decides to station the ambulance. The environment then samples the patient request location as the new state, and the reward in that situation was the transportation cost. The time horizon of each steps you can think of as the 24 hours in a day, the number of times that this process is repeated, and then each episode is repeated k times, which you could think of as the kind of number of days in the year potentially. And then the goal in general reinforcement learning setups is for the agent to try and learn a policy that maximizes their cumulative reward. Now, common to a lot of these reinforcement learning tasks are these Q function and value functions and the Bellman equations that relate them. So the Q function is defined to be the expected future reward that the agent receives taking a given action from a state. And so that's defined as the immediate reward that they receive plus the expected future reward that they will receive having taken that specific action in that state. In the ambulance example, this would be the transportation cost that they pay initially while having to travel to that specific location. And this expectation will be the transportation cost that they experience when they have to interact with the environment starting from the location that they had traveled to. The value function is then defined as the future reward that the agent receives starting from a specific state and following their policy. So it's just defined to be the expected sum of the rewards that they will experience. And common to these dynamic programming problems are the Bellman equations that relate these quantities across different steps. So the value function is defined to be the Q function for the action that the policy says to be taking in that specific state. And the Q function is equal to the immediate reward that the agent experiences plus the expectation of the value function over the next step, where the value function at the end of the day is defined to be 0. And now, if we knew the dynamics of the system, if we knew what the reward function was, if we knew what the dynamics were so we could compute this expectation, we could just solve these Bellman equations in order to learn what the V function and the Q function are, where we use the fact that for the optimal policy, the value function takes this alternative form where the value is equal to the maximum value of the Q function. But in online settings, we're not able to solve these equations exactly because we have a lot of different problems that we experience when we're interacting with the environment in an online fashion. And so in an online setting, we don't have access to a simulator. The reward function and the dynamics of the system are unknown, and the agent is going to be penalized for suboptimal actions that they take until the end of the episodes, which takes 8 steps. And what this kind of means from an algorithm design standpoint is because we don't have access to a simulator, it means that we have limited information. And so we can't simulate trajectories of the process, which is common to a lot of prior work. And because the reward function and the dynamics of the system are unknown, we have to estimate these from the data, but the data is also collected adaptively on an online fashion. And the third requires that we partake in the exploration-exploitation trade-off that is very common in multi-arm bandits. The goal in this situation, instead of trying to maximize the reward, you can instead try and minimize the regret, which is defined to be the sum of the value of the optimal policy subtracted away from the value for the policy that the agent plays. So this is how much regret that the agent experiences for playing their specific policy versus the optimal policy. And so in a lot of operations research problems, we found that they have very large or continuous state and action spaces. And kind of the first question that you would have under these settings where the state and action space is large is how you can try and incorporate structure. And so what we choose to do is assume Lipschitz smoothness on the model, but obviously there's a wide range of approaches that you can take, spanning from parametric to non-parametric approaches. On the parametric side, some things that you could do is to approximate the different quantities with a linear function or approximate them with a neural network. The downside to these approaches is it requires strict parametric assumptions, and obviously you're going to incur a loss if your model doesn't fit these very specific assumptions. On the other kind of side, you have these non-parametric assumptions where you can either approximate things with local smoothing or you can use kernel methods. The downside to these approaches is that it can be very expensive in terms of both memory and sample complexity because it's often exponential in the dimension. Ideally, you would want to live kind of somewhere in between non-parametric and parametric, but this paper we will be talking about approximating with local smoothing. And so the second kind of question, if you're going to approximate with local smoothing with a non-parametric approach, is how you can try and reduce the memory requirements of common reinforcement learning algorithms. You can think back to the earlier examples that I proposed of the dynamic cache management system. Obviously, an agent in this situation has to fit on a tiny little chip. So how can you reduce the memory requirements of these algorithms in order to make them be able to scale to actual problems? So if you have a large or a continuous state and action space, kind of a naive solution is to try and discretize the state and action space uniformly. And what this ends up doing is it takes your continuous Markov decision process and maps it to a tabular or a discrete one. And the way that you do it is just with a fixed discretization. So back to the ambulance example, the state space was the location of the ambulance, so the interval 0, 1. The action space was the place you want to move the ambulance to, also the interval 0, 1. And so we pick a fixed discretization of the space based off of some parameter epsilon. Then you pick epsilon as a function of the time horizon in order to balance the approximation error that you get from taking your continuous process and mapping it to a discrete process versus the cost of solving the discrete process, because we already have algorithms that are able to solve reinforcement learning tasks for a discrete space. But the problem with this approach is that it wastes a lot of memory, and it also wastes a lot of time learning because it creates a lot of unnecessary exploration, because every single point on this discretization needs to be checked. And so it wastes memory by discretizing suboptimal parts of the space because you have to check every single part of the space And if the region is really bad, then you don't even need to discretize there because it's not important for the optimal policy. And lastly, the learned policy does not adapt to the underlying geometry of the space because you're forced to this fixed discretization. And so what our approach is to instead is to try and preserve the performance of this optimal epsilon discretization, but reduce the memory requirements of the algorithm. And so what we do instead is, instead of picking a fixed discretization, we make a sequence of discretizations where we only continue to discretize this space on an as needed basis. And so we initially create a coarse discretization before continuing to a slightly more fine discretization, and the process then continues. And so to highlight kind of what the algorithm is doing, instead of just showing some pseudocode, I want to walk through an example. So again, let's pretend we're on the Las Vegas Strip. So the state space was the interval 0, 1, and the action space again was the interval 0, 1. Here, plotted in the gradient, is the Q function that I talked about earlier, which was the immediate reward plus the expected future reward that you get, where green corresponds to a high Q function or high reward, and red corresponds to a low Q function. So because we want to maximize the Q function, the optimal policy in this situation is along the diagonal of the space. So if you're in this specific state here, the optimal action to take is the one that intersects with the diagonal. So what our algorithm does is, initially, it keeps a very coarse discretization of the space. So here we have taken the space and split it into 4 different regions. Along each of the regions, we maintain upper confidence bound estimates of the Q function. And this is something that's common for multi-arm bandits, where you maintain upper estimates of the related quantities that you're trying to solve for. With these estimates, you select the relevant region that maximizes these UCB estimates. And so what does this relevant region mean? If you're in a specific state here, let's say the state like 0.1, the relevant regions are these 2 regions above it that it intersects with. And this one has a value of 1.4, this one has a value of 1.7. And so the relevant region that we pick is this one in the top left corner. We pick any action that's within that region, and we update our estimates with the newly collected data. And how we update our estimates is presented at the bottom here. And you can think of it as taking a linear combination of the old estimate plus a combination of the observed reward, a bonus term, which again is very common for multi-arm bandits, and an estimate for the future value for being in the next state. And this you can kind of think of as an empirical version of the Bellman optimality equations, where the Q function is defined to be the immediate reward plus the expected future reward, and the value function is equal to the maximum of the Q function, where instead we're taking the Q function is equal to an empirical reward plus an empirical expectation. With this, the process then repeats, but kind of the main kick of our algorithm is deciding when we want to subpartition a space. And so what we do is we subpartition a region when the confidence radius in its estimate is smaller than the bias that it experiences. And you can write down what it means mathematically, and it corresponds to the number of times that you are within a specific region is larger than 1 over the diameter of the region squared. And once you subpartition a region, the new regions have half of the diameter of its parent. So initially, our partition looks like this. And once we've decided we need to subpartition, we split that specific relevant region into 4 different sections. This process then repeats until the end of the episode, and hopefully you are converging to learn the optimal policy. And what we tend to see with our algorithm is that our algorithm zooms in on the promising regions of the space. And what that does is it reduces exploration in suboptimal regions as compared to a uniform discretization. And so here we can see that our algorithm is not discretizing the red parts of the space, which is where the Q value is relatively low, whereas a uniform discretization would keep a fine discretization of this part of the space and force the algorithm to check those points. Moreover, we see that the gain in memory and the speed in learning of our algorithm depends on the underlying functions. And the key part of the analysis is to show that the suboptimal regions of the space are quickly determined to be suboptimal and thus are not selected or further discretized. And we are able to show a theoretical bound on the regret for our algorithm, which scales kind of based off of these 2 terms. The first term is h to the power 5 halves, where h is the number of steps. The second term is k, which is the number of episodes, to the power d plus 1 over d plus 2, where d is a covering dimension of the state and action space, which If your state and action space is in the Euclidean space raised to the power d, then d is the same d that you have in the regret bound here. What is nice about our algorithm is that we show that we have the optimal dependence on the covering dimension by mapping it to lower bounds from contextual bandits. Moreover, we match the regret bound for the discrete setting where you use a discrete metric on the space, and the algorithm matches our intuition where the worst case performance matches the uniform discretization argument. Just to kind of help illustrate what the algorithm is actually doing, I've prepared a little bit of the simulation. So again, this is back to the Las Vegas interval 0-1 ambulance experiment. And here we have 3 different plots. We'll talk about them one by one. And so on the first plot, the plot on the left, we have a comparison of the observed rewards between the adaptive algorithm in green and the uniform mesh algorithm in red, where the y-axis is the observed rewards and the x-axis is the episode, so the time. And what we see from this plot is that the adaptive algorithm is quickly able to learn the optimal policy and maximize their rewards, whereas the uniform algorithm lags a little bit behind. The second plot, we have a comparison of the size of the partition, where here the uniform algorithm has a fixed partition size, and the adaptive algorithm, obviously the partition size is increasing. We see that it increases at a much slower rate and is much smaller than the partition that you would need in order to learn the optimal policy for fixed discretization. And in the third plot, we have the actual discretization that our algorithm is producing over the course of learning. And so just to play it again, we see initially it starts with the coarse discretization before it quickly zooms into this dark green region, which corresponds to high expected future rewards. So this again matches our intuition of the algorithm that we are only discretizing important parts of the space, and we are not discretizing suboptimal parts of the space, which correspond to the red regions along the outside. And while this is only one experiment, we have numerous simulations that are showing very similar results. Some ongoing work that we're currently working on is what if the metric on the space is not known a priori? Can you try and learn the metric online while also learning the optimal policy and discretizing the space? The second question is, can we extend this adaptive partitioning technique to other decision-making tasks, which is something that we're currently working on. And the third question is to try and gain gap-dependent bounds, because the current regret bounds that we have are kind of worst-case problem-independent bounds. And just to kind of review the main contributions that I mentioned before, we were able to develop an efficient algorithm for reinforcement learning in large state and action spaces. And our algorithm is able to reduce the memory requirements of common reinforcement learning algorithms by only discretizing important regions of the space, which we saw both in the theory and also through the simulations as well. And so thank you so much for watching my presentation. I've included the citation for the paper here and also my email. Feel free to reach out if you ever have any questions. Thank you.